the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students or perhaps pre-calculus students who are learning about matrices and matrix arithmetic and all the stuff associated with basically computational matrices here. And in this video, we're going to talk about how to add two matrices and how to multiply a matrix by a scalar. And luckily, because matrices are essentially like a collection of column vectors, and we know how to add vectors, the definition of adding two matrices will be very, very familiar to us. If A and B are both matrices of the same size that's required, then their sum is defined to be the same size matrix where the ijth element of that matrix is the sum of the ijth elements of the matrices A and B. Essentially, this is just saying add like entries. For example, if matrix A was 1, 2, 3, 4, and matrix B was 5, 6, 7, 8, then their sum would take corresponding elements and add them. For example, 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. And I'm just seeing if you're awake, that's actually 12. There's not much else I can say about that because it's pretty much self-explanatory, right? That's somewhat obvious to most people. The most important thing here, other than just knowing how to add two matrices, is that you can only add matrices of the same size. Therefore, it would not make sense to add these two matrices right here. The first one is a 3 by 2 matrix. The second is a 2 by 2 matrix. They cannot be added. They just don't have the same size. Now we're going to talk about the scalar multiple of a matrix, just basically how do you multiply a matrix by a number and how do we define that? And it's pretty obvious because the way we define scalar multiplication of vectors was to multiply every entry in the vector by the scalar. Well, the same thing is going to be true for a matrix. If K is a scalar and A is an m by n matrix, then the scalar multiple of A, denoted K times A, is the m by n matrix whose ijth entry is K times Aij. For example, if we took our trusty matrix A, which is 1, 2, 3, 4, and we want to look at, let's say, negative pi times A, well, that would just multiply each entry by negative pi. Not much else I could say about that. It's yet another somewhat obvious definition, one that we would all agree is a very nice definition. Did we have to define scalar multiplication this way? Well, not necessarily. However, how we define the scalar multiplication has to satisfy some axioms in the background to make our arithmetic actually work. But luckily, we define scalar multiplication this way. It makes sense to our brains. Now, speaking of axioms, it is very important that we set up some background theory about what is true. Like, could we add matrix A to B and will that become the same as B plus A? Or if we associate the summation slightly differently, let's say this guy right here, is that summation the same? Remember, in the last video, we defined what the zero matrix is. And so is it true that A plus 0 is equal to A? So anyhow, this theorem right here tells us that all of these statements are actually true, and we're going to prove one of them. But these should look very familiar to you. These are pretty much the same as the arithmetic properties of vectors. Now, because I'm going to prove one with associativity later on, I'll go ahead and actually prove the one with addition associativity here. So essentially the associative property of addition for matrices. And by the way, if you read the theorem, which I didn't bother reading out loud, A, B, and C are matrices of the same size. The zero matrix should also be of the same size. And R and S are just scalars in our background field. Or number system, if you like that word better. Proving one of these, specifically B, I'll start with the consideration of the left-hand side. Now, before I start, I should state like some major suppositions here, that A, B, and C are matrices of the same size, and that R and S are scalars, even though we're not going to use R and S here. So I'm just going to go ahead and highlight this statement right here saying, let's go ahead and assume that A, B, and C are of the same size. Now, what's going to be slightly different about this proof versus most proofs up to this point is that I need to step a little bit outside of this structure right here. That is, instead of working with A plus B in quantities plus C, I'll consider the ijth element of A, the ijth element of B, and the ijth element of C. So let's start here. I'm going to do something that will seem kind of weird to you. I'm going to let the matrix D equal the sum of the matrices A and B. It just will make sense in a moment. Then the ijth entry in D is, by definition, the sum of the ijth entry of A and the ijth entry of B. That's just by the definition that we set forth in this video already. Moreover, the ijth entry of D, and remember, we're saying that this right here is D, so the ijth entry of D plus C, well, is the ijth entry of D plus the ijth entry of C. But we just said what the ijth entry of D is. It's A sub ij plus B sub ij. So I'm just making a substitution. D sub ij I'm replacing with A sub ij plus B sub ij. These are real numbers or scalars, and so we can rely upon our good old arithmetic properties that we know of. We can reassociate the addition. We can use the associative property of addition for real numbers, or for scalars, if you will. And so I'll regroup this. Now I'm going to do what we used to do back in, let's say, a trigonometry course. Back in trig, you would start with one side of an equation, and then if you get stuck, which we're not stuck, but I'm just telling you that some people do this, you'll work on one side of the equation, get to a certain form, and then you'd switch to the other side of the equation and try to get to the same form. And that's exactly what I'm going to go ahead and do here. It's a little bit easier to see the proof this way. So what we started with was the quantity A plus B and quantity plus C. And then we let D equal that A plus B, and we mentioned what the ijth element of D is, and then we said, therefore, when we add matrices A and B, and then add that to C, the result is this business right here. Now let's consider that right-hand side. What if we were to add the matrix A to the summation of the quantity B plus C? We're going to let the new matrix E just be the sum of the matrices B and C. Then the ijth element of E is just the ijth element of B plus the ijth element of C. And so the ijth entry of the matrix sum A plus B plus C, which is the same thing, by the way, as A plus E, is going to be, well, the ijth entry of A plus the ijth entry of E. But we know the ijth entry of E is B sub ij plus C sub ij. And note where we've arrived. The ijth entry of D plus C, which is the same thing as the quantity AB plus C, I should have written that down there, is the same thing as the ijth entry of A plus E, which is A plus the quantity B plus C. I'll write that down. Now that we've have that written down, that the ijth entries of all those summations are exactly the same, that means those matrices must be equivalent, or those summations must be equivalent. Hence, the quantity A plus B and quantity plus C is the same thing as the matrix A plus the quantity B plus C. That seems very convoluted, but it's pretty rigorous. We're just talking about the ijth elements the entire time. We're really trying to get through and just say, no matter what, whatever position you're looking at, that entry of the left-hand side of this will match that same entry on the right-hand side. So we just compare the ijth entries. I and j are arbitrary, so every entry in those summations must be the same. Now, I took my time with that. There are some cleaner proofs for that, but really, I was just kind of straightforward going through and doing it. But I think that's a pretty nice proof and a nice understandable way of doing it. And so that will do it for this video. That's all I really wanted to do, was go through and talk about how to add a couple matrices and talk about the properties of matrices, which are right here. I didn't go through and talk about each one of them, but you can see them on your screen. It's very important that you get comfortable with these. And I'll give some warnings in a future video on multiplications, but scalar multiplication is defined like this, so that works out perfectly. But when you go to matrix multiplication, which we will, it is a little bit more challenging and some of these rules do not work. For example, commutativity of matrix multiplication is a bit broken. So we'll talk about that when we get there. But that does it for this video for now. I hope you guys have a wonderful day. I hope this helped you out. Be wonderful humans.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.